Hey, what's up, everyone? It's no surprise that I love capture the flag challenges. Heck, they're the majority of the content on this YouTube channel. I think they're a great way to learn different concepts about cybersecurity or computer science. I think they're great just for fun and teamwork and building up different skills in reverse engineering or ethical hacking. But sometimes capture the flags don't quite scratch the itch. Sometimes you want something uh, realistic, I guess, some actual software that you can dig into and tear apart, not a challenge that was created by someone that's intentionally vulnerable. Sometimes you want to be able to actually find vulnerabilities in real world software. And if getting started with like kernel exploitation or anything like that is too much and you need to take a step back, a great way to do this is going to exploitdatabase.com, which I've pulled up right here. And if you're not familiar with it, it's just basically a database or repository of a bunch of open source proof of concept exploits for different software, right? And we can come here and we can toggle and look at all the different platforms they have. We see all the different flavors of Linux. We see Windows. And we see right here, there's two buttons. There's verified and has app. Verified just means that the exploit or the proof of concept is guaranteed to work. And then has app means that there's a link to the actual vulnerable piece of software. So downloading some of these and kind of putting on your investigative cap and trying to be a security researcher or vulnerability researcher and looking at like, hey, how can I find that vulnerability myself and write my own proof of concept exploit is a great thing to do to boost your skills and whatnot. So I've already pre-selected an exploit, or not exploit, a vulnerable piece of software here, Dup Scout Enterprise. We can see just by the title that there's a buffer overflow vulnerability in the login feature, or the login functionality. And the proof of concept code here is written for a Metasploit module. So what I would implore you to do is to find something similar or follow along with me on this video and just look at the title, nothing else. Don't scroll down and read the exploit code. Use that as almost like a reference or a cheat sheet if you get stuck, but just download the vulnerable application, install it, and try to do your own reverse engineering or static or dynamic analysis and find the vulnerability. So that's what we're going to do in this video. So this is an actual piece of software. It's not a capture the flag or anything like that. It's not intentionally vulnerable, but hey, this is a great way to kind of boost those static and dynamic analytical skills. So we're going to click here and download the app. And you see I already do have it installed, but sure, I'll save it again. And once that downloads, we can open it up. And it's just going to be your standard Windows installation wizard. And Windows Defender is going to warn me saying, hey, this isn't a legit Microsoft app. We don't trust this. Are you sure you want to install this? So we're going to say, yeah, just install it anyway. Look through these prompts. And yeah, this is just your typical installation wizard for setting things up. And I do get a warning, hey, you already have this tool installed. You already have this application installed. Are you sure you want to replace it? I'm just going to click no, but you would click yes just to get it up and running on your computer. And after that, we can just search for Dup Scout and we get our client. So we want to connect here. And that looked like it worked. It looked like we were successfully connected. And you can go to options, and I already have this enabled, but you might have to enable it yourself. If you go down to server, there's this option here for enable web server on port. This will be unchecked by default. We want to enable this. You can use any port you want. I'm just going to use the default port 80 because that is the standard HTTP port for web communication. So click save. Now we actually want to interact with that web server. So I just type in HTTP ://127.0.0.1. We see here it brings us to Dup Scout Enterprise status page, and we can see my local working directory that is selected. And I didn't even explain what Dup Scout is. It's a piece of software that will go either on your own computer or if you have it installed in a network or like an enterprise corporation, it can find duplicate files and erase those. Because if they're just duplicate files, if they're just copies, they might be taking up valuable space, valuable resources on that hard drive. So all it is like a disk space cleaner. But from the exploitdb title, we see that there is a buffer overflow somewhere. So now we're going to try to find it. And we know it has something to do with the logon functionality. So we're going to click here on login. The default creds are just admin and admin. So right now we're not going to try to fuzz it. We're just doing the bare bones basics. Hey, trying to understand how this software even works, what functionality and what features does it have. So now that we're logged in, we see this menu at the top for home and settings and help and about, and we can also log out. So this is pretty cool. Since we know there is a buffer overflow somewhere in the login procedure, we have two options. We can either fuzz the username or we can fuzz the password field. It's not likely that the password field will have some type of buffer overflow vulnerability. I guess it could, but passwords are usually hashed and stored in a database, whereas usernames are just saved and stored as clear text. So I would be willing to bet that there is some type of exploit or some type of flaw in the username field. So we can test it here just by slamming in some A's. And it says the specified username and or password is incorrect. Okay, so just fuzzing through this, it's not really ideal. We can knock ourselves out. However, I think using something different or a tool specifically designed for this feature or for this task would be a lot easier. I'm going to use Burp Suite for this. So I have Burp Suite Community Edition installed here on my host machine. If you're using Kali Linux or anything like that, Burp Suite Community Edition will be installed by default. So there's a few ways to actually use Burp Suite. You can use a proxy, right? And if you're using Firefox or Chrome, like whatever web browser you're using, you need to enable the proxy settings, or you can use Burp Suite's own browser. So I'm just going to click here on Open Browser, and we should get a pop-up pretty soon. Here we go. So now we can type in a URL. So once again, we're just going to go to localhost, and it did bring up the login page or like this screen. However, it seems like it didn't load like all of the HTML or all of the CSS, because this isn't as pretty as the other one was. If I click on login, yeah, we see this is very like tempered down. It's not very pretty to look at like the other one was. But nonetheless, it should have the same functionality. So I'm just going to type in test for the username and the password. And now I'm going to click on login. Okay, the specified username and our password is incorrect. So we're going to click here and we're going to go to targets. You can see the different requests that we made. So we look at the post request. So we're actually sending data to this login form. And I know that's super tiny. I don't know why it's so small. But you can see that we made a post request to /login, and we specified test as the username and the password. I'm going to right click here and go send to repeater. And this just allows us to easily play around and send multiple responses to the website. I can change up the username, and I can change up the password, and I can send it in here. So we want to fuzz this username parameter. And there's a few ways we can do this. I'm just going to slam in a bunch of A's, a bunch of random characters to see if we can crash this program. So there's a bunch of ways where you can generate random data. I'm just going to use Python since we're doing something very simple. I'm just simply going to say A times 1,000. And that's going to give me 1,000 A's. I can come here and just copy and paste it in here for the username field. Now I'm going to hit send. And it's been a while. We don't have any response back from the server. So it seems like maybe we crashed it. If I come back here and I refresh the page, okay, it looks okay. Let me refresh it one more time. All right, now it can't be reached. And if I do the same thing here in Chrome, or in the Burp Suite browser, we see we get an error. It failed to connect to localhost port 80. It looks like we did, in fact, crash the service. Sweet. So how can we analyze application crashes on Windows? There's a few ways, but the most, I guess, the first one I thought of is looking at the event viewer. So looking at the actual application event logs that Windows records. I guess on Linux, an equivalent would be analyzing the dmessage output. So I have event viewer opened, and we're just going to click here on Windows logs and then application log. Let's make this a little bit bigger and easier to read. Okay, so just clicking on some of these random ones. You see here it says event name app crash. So something has crashed. We see the name of our executable, Dup Scout service.exe. Okay, I don't know if these are values of registers or what exactly a P1 through P10 is. We can see the crash dump or the core dump. I wonder if we click on this. Event viewer can't open this link. Okay. If we really wanted, we could examine this further. Let's keep looking. So this is an information log. Let's click here on this error log. Okay. So this is the same process that we've crashed. Fault offset, not sure what this value is. I guess let's just keep looking through some of these. Information, error. Oh, here we go. So when we click on this one, we see the fault offset is hex 41414141, which, if you're not familiar, OX41 is the hex value for A, capital A. We sent 1,000 capital A's. So it looks like we've overwritten some type of offset, maybe the instruction pointer or the return address. So let's play around with this more. Let's, since we've crashed the service, we need to open up the services menu and navigate until we can find Dup Scout Enterprise listed here. And now we want to restart it. Start it back up again. It's a little bit tedious, but hey, we'll have to do that every single time we cause a crash. So now if I refresh this page, the service is back up and running. Now I can log in with admin and admin. But now let's try to find how many bytes of junk. So I threw 1,000 A's at this to cause a crash, but our end goal is to get some type of remote code execution, right? Always keep that end goal in mind. In order to get remote code execution, what will we need to do? First, we need to find the offset of how long it takes to get to the return address. So once we can control where the return address will point to, we can have it point to our shellcode, right? Because we want to get either some type of reverse shell, or we want it to open up a port on the target that we can connect into. We want it to do something, I guess, malicious or unintended with our shellcode. But the first step is identifying how many bytes of junk or random data it takes to get to that return address that is on the stack. So a great way to do this is if you search for pattern overflow or pattern buffer overflow, something like that. Google, one of the top results should be from wiremask.eu. And we can see here, we can generate a pattern. This tool supports 32-bit and 64-bit registers. Awesome. So the default length is 200. Let's crank that bad boy up to 1,000. And we can see here that it generated this pattern. So we're just going to copy this. We're going to come back to our Burp Suite now. And we're going to take this out. I'm just going to say test and test just to make sure this is up and running. Yep, everything works. So now for the username, let's slam in this unique pattern. We hit send. We get no response back. Come here and we verify that the service has crashed. Ooh, it looks like it's good. Let's see. Let's come back here, refresh the page. Okay, so it has crashed. Maybe it took a little bit. So now if I open back this application event log, I click out of it, click back into it just to refresh it. It looks like it has crashed again. You see that the date and time is updated. And we go down to the error log, we can see a new fault offset, right? Before it was OX414141, and now it is this. It's this different value. So let's copy this and come back to our website, our wiremass.eu, and where it says find the offset, let's paste in that register value we found. And we see it says 780. So it takes 780 bytes of junk to get up to the return address. So once again, we need to restart the service. And forgive me if I'm going very slow, but sometimes you never know. You never know who's watching the video. You never know anyone's experience level with buffer overflows. And this isn't a capture the flag, so there isn't any detailed write-up or walkthrough available, since this is like real world software and whatnot. So I figured a nice detailed, gentle introduction walkthrough would be appreciated. But hey, I'll leave timestamps in the video just in case I am going a little bit too slow for the more advanced users. So now we want to paste in, and this is just a, I guess we're just verifying that it does take 780 bytes to get to our offset. So now I'm going to come to our pattern. I'm going to change this to 780. Now in Burp Suite, I paste in 780 bytes of random junk. And then I'm going to paste in or type in 4 X's. So now when I cause the crash, we should see in the application event log that the fault offset is overwritten with hex 58585858. Because that means our 4 X's successfully overwrote that return address. And there it is. OX58585858. Sweet. So now we know exactly how many bytes it takes to overwrite the return address. So now we can change this. Instead of just being some random characters, we want it to be a position that will go to our shellcode. So we don't know much about this binary. We don't know if it has ASLR, so the addresses are being randomized. We don't know if it has SEH enabled, structured exception handling, which is Windows like way of handling errors like this and application crashes. And there's mitigations to get around that. We don't know really much about this binary yet. So there's a few tools we can use. I didn't know if there's like a check sec or anything like that for Windows. I couldn't really find it. But I do like Radare 2 and its suite of tools. So let's see if we can use that. I have Windows Subsystem for Linux running here. So once this finally opens up, geez, is it taking its sweet time? There we go. I do have Robin 2 installed. And we can use this to analyze our portable executable just a little bit further. So from Windows Subsystem for Linux, I can access my Windows drive as well. So this is where the file is located. So let's actually type this in here. I'm just going to navigate here with CD. So here is where our service is installed. Let's do Robin2 tech capital I and Dup Scout s.exe. Make sure this is nice and big for everyone to see. There we go. So we see the architecture. It is 32-bit. Here is the base address of the binary. That could be good for later on. It says it does have a stack canary. That could be problematic. These other protections are turned off. You can see the date it was compiled. It's pretty old, 2017. It's a little Indian. Okay, so it's not NX. It's not non-executable, so there is no data execution prevention, so we don't need to do anything like return-oriented programming, which is really nice. Operating system is Windows. We knew that. Doesn't have position-independent code. There is some type of reallocations going on. Okay, so the binary itself that has the base address of OX400000. So this will stay the same, but there is some type of ASLR going on. I'm reading this correctly. That's what relocate means. The binary is not signed by Microsoft. We knew that because that's why Windows Defender was like saying, hey, are you sure you want to install this? The binary is not stripped of its debugging info. Okay, so I think we're good here. So now we want to figure out what address we want to overwrite the instruction pointer with, and then we can shellcode. So if you wanted, you could disassemble this, but I think just opening up a debugger will be more than enough. So I'm going to use WinDbg or WinDbg, Community Debugger, or Ollie Debug, or x64 Debug. That will work just fine. All you need is a Windows-based debugger. There's a few of them, and I'm just going to be using WinDbg. So we have that opened, and there's two versions. There's x86 and x64 for WinDbg. Since this is a 32-bit binary, you want to use a 32-bit debugger. So we're going to go to File, Patch to Process, and these are time sorted. So things that started first on the system will be here at the top. That's why we see things like system and secure system and everything like that when init. And then things that started more recently will be at the bottom. So we can scroll down here and we should see our Dup Scout towards the bottom. And if my eyes are failing me, I can click on this filter to sort by executable, and now they're in alphabetical order, and that's just a little easier for me to find. Actually, I don't see it running here at all. I don't think I restarted it. Let's restart the service, because we did crash it, right? Now if I go to by system order and go all the way down to the end, you see our Dup Scout. If I click here, if I click on this plus sign, we get an error. And if I actually click OK and try to attach my debugger to it, it fails. Could not attach to this process. Access is denied. And that's because I goofed up. I ran WinDbg, but I didn't run it as admin. You're going to right click and run as administrator. You click yes. And you want to do that same process again. So let's go back to File, attach to a process, scroll all the way down. And now when we click on this plus sign, we can see that it gives us actually detailed information about this binary. It gives us the full file path and the user is running as. Now when I click OK, that's the process, go down to the end. I don't think you can click on this. I think you see here how the process ID is blank. I think you need to actually click on this process. Now click OK. There we go. So now we have successfully attached our debugger to that running process. Let me see if I can crank up the font size so it's a little easier for you guys to read. There we go. Hopefully that's better. You can see here that it did insert its own breakpoint inside of the process. We can just hit G to continue, and now the binary is running and the process is running as normal. Come here, we can refresh, we can log out. So now we can just use it regularly. Cool. So we want to actually send junk to this, and we can keep using Burp Suite if we want, but I'm kind of over this. So I'm just going to exit Burp Suite, and let's actually open up Visual Studio Code, and let's write some Python code. Let's make an actual proof of concept script so we can start sending our exploit and whatnot to the service. So I know I'm going to need the Quest module, quests, and what is the URL? I'm just going to copy the URL from here. And we know we want to send a post request to that URL. And the post request is going to need some type of data. So data equals data. So now we need to make a dictionary. We have the username field. and we have the password field. For username, this is the thing we want to fuzz. Let's leave that blank for now. For a password, we'll say please sub, which hopefully if you're enjoying this video, you've considered subscribing if you're not already. So in the username field, we want to send our payload. So let's start building the payload. So we know it takes 780 bytes of junk for our padding. And we can do 4 Bs just to overwrite the instruction pointer, overwrite EIP. And this isn't absolutely necessary, but I'm curious how many bytes of data we have after the instruction pointer overwrite. Let's send about like 400 Cs. And this will make sense in a second. So let's look at this. Save this as exploit.py. Okay, so we have our URL, localhost, the login page. We have made a post request to send to that URL. And for the post data, we're going to be sending the username will be our payload. So we're going to fill up the buffer with junk. We're going to overwrite the instruction pointer. And this is just a placeholder for now. And then we want to see how many bytes after the instruction pointer overwrite that we control. And we can add some like helpful like debugging info and whatnot. Let's do this. Sending payload. Print out the response if we need to as well. Let's save this. Open up a command prompt. Where did I save this exploit to? Okay, there we go. All I did was change where this file was located. I had it stored in like some other folder on my system. So now I made a very simple working directory, Dup Scout Enterprise, and you see my exploit right there. So now let's actually run this bad boy, Python 3 exploit.py. It doesn't like my syntax. What did I forget? I need a comma here because this is a dictionary. Up arrow, enter. Okay, it's taking its sweet time. Right, so now it's sending the payload. Okay, so we see here in the debugger that it has crashed, right? Access violation. And we see here the instruction pointer has been overwritten with our B's. If I do ddesp, you can see that our C's are on the stack. Let's do ddesp L60. Okay, they're still there. L80. Cool. So this is how many bytes of data we control after the instruction pointer. So this isn't a huge deal. This is where I'll put my shellcode. But for example, if we didn't have this many, like what I have highlighted, like let's say this is all we had, and then the stack runs out, right? So if we only had a few bytes that we control after the stack, then what we would want to do, and instead of putting our shellcode here, because this is just a placeholder, we would put it inside of where our padding is. So maybe we have like 400 bytes of shellcode, and then like another 300 whatever bytes for the padding, so we get to the instruction pointer overwrite. But right now, what we want to do is replace these B's with an actual address of the stack, right? So we saw that ASLR is enabled, because if we can just overwrite the stack, if we can overwrite the instruction pointer with like something like this, and just have it return execution immediately into our shellcode, that would be a great win. But ASLR, I think, is enabled. And anyway, these addresses start with the null byte. How do I look at registers? I'm so used to GDB that I've forgotten debug. It's a little sad. Just a little bit sad. But anyway, so what we want to do is be able to find some type of instruction that will allow us to just jump to the stack pointer. No matter what address the ESP is, because this will change, we want to be able to jump to it. So we want to find some type of instruction or gadget, and a great tool to do that in WinDbg is Mona.py, created by Corlan Coder. It makes really, really great resources for Windows binary exploitation and security. So we have this old GitHub repo. You can see the first commit was like 12 years ago. That's ancient. However, this still seems to be like the industry standard tool, or at least what I could find for hobbyists and whatnot online. That seems to be Mona.py is like the go-to tool. So we can see Mona.py is a Python script that can be used to automate and speed up specific searches while developing exploits, typically for Windows platforms. It runs on Immunity Debugger and WinDbg, and it requires Python 2.7. And that's a fact. It will not work if you have Python 3 installed. So what I had to do after some troubleshooting, I had to go install an older, outdated version of Python, Python 2.7. And once I had that up and running and added it to my path, I was able to get this working. So it does run on 64-bit WinDbg. The majority of its features were written specifically for 32-bit processes. And that's okay, because today we are looking at a 32-bit process. And for more info, you can check out his website here. So if you're using Immunity Debugger, which I believe is no longer really supported at all, I think it's now x32 debug or x64 debug. I believe that's the open source successor to that. But we'll be using WinDbg, so we need this WinDbg lib resource. So we come over here, and it's equally very, very old, right? The last commit was 3 years ago, and the first commit was like 12 years ago. In order to get Python scripts running in WinDbg, you do need this tool called PYKD. I'm not really sure if that's an acronym or what it stands for. And trying to find it, it does link to a Russian website that is like taken down. Like if you go to the URL, it won't resolve anymore. So that's pretty sketchy. However, this tool itself is legit and it's fine as far as I can tell. And it's just a zip file, and you can analyze it if you want. If you follow along with the different installation instructions, you will be good to go. We'll be using this one because I have a 64-bit host operating system and I'm using a 32-bit debugger session. So just walk through the steps that he has outlined here. And if you do run into any issues, because it can be a little bit problematic, just hit me up in the comments and I'll do my best to answer. But I already have this installed, so I'm just going to skip this step, but I will leave a link to all of this in the description down below. So inside of my WinDbg session, I'm going to hit period load pykd dot pyd. And after that, now I have the ability to run Python scripts. So I'm going to do exclamation point py and then Mona. And this should print out the help information. Yeah, there we go. If I scroll up to the top, you can see that it is running Mona.py. You see where it's installed on my system. This is a Swiss Army knife for exploit development on 32-bit Windows, and it has a very pretty banner and everything like that. So we can see some options up here. Just some flags and whatnot to specify bad characters or modules and whatnot. But here is what we are most interested in, the available commands that we can. So it has a lot of functionality, and it can help you find gadgets and whatnot to get by, for example, safe SEH or structured exception handling and raw. And it can create pattern offsets. So we used a website to do this, but you can also just use Mona to create a pattern and find the offset and whatnot. But what we're interested in today is this command, the jump command. Find pointers that will allow you to jump to a register. Let's run that. Let's do JMP, see if we get some help information. So mandatory arguments are tech R. Then we need to specify what register we want to look for. So we want to look for ESP, stack pointer. You can see that it's running. Just let it do its thing. And so that didn't take too long at all. So it found a total of 15 pointers. And we can see here that it has written the output to jump.txt in my working directory. Now, by default, I don't think it will have a working directory or like an output file. I think you need to set that yourself. And then you would run this config command and you can specify where you want the output to be. So if I do open up this file, if I do notepad jump.txt, we open this up, we can see it just has the output that we saw in mona.py. So it's actually really nice, right? It tells you the info about the different modules, what security mitigations it has. So for example, Net API 32, maybe this wouldn't be the best module to take gadgets from because it has security mitigations like control flow guard and ASLR turned on and non-executable. So we want to find DLLs that don't have those mitigations just to make our life a little bit easier. And we do see a lot of instructions for pushing the stack pointer onto the stack and then returning to like offset of that. This is fine, but I think we can do better. I like this jump instruction right here. Just go directly to the ESP. Because that will change because this binary has ASLR enabled, address space layout randomization enabled. So no matter what value the instruction pointer, the stack pointer has, just jump to it. I like that better than pushing it onto the stack and jumping to it actually. And we can click here and we see what module. So libspp.dll. And it doesn't have any security mitigations enabled, which is pretty sweet. So I'm just going to copy this. I am going to add it to our exploit code. So I'm going to make a little comment here, paste that in there. I'm going to copy this, come back to WinDbg, and I'm going to do U, paste in that address, just to confirm, sweet. So it is a jump ESP instruction. So Mona was not lying to us. But we do want this. I'm just going to exit out of WinDbg while we clean up our script. So we want to change a few things. We want to change this EIP overwrite, and we want it to be struct.pack little endian integer for this address. So we need to actually include this module. Let's just say from struct import pack. And all that does is take a hex value and it will create it, and it will convert this hex value to the correct byte representation. And since we're using Python 3, we can't concatenate bytes with strings. So we need to add a little b in the front here. This looks good. This looks good. Let's restart our service just for the heck of it. And while that's restarting, let's open up WinDbg as admin one more time. You see how tedious reverse engineering, exploit development, and things like that can become. Let's type in G. That's just to run or continue the program. If you're familiar with GDB, it'll be run or continue, but WinDbg is different, so it's G. Let's rerun our exploit code. You know what? I did not actually set a breakpoint. So I just ran it and it crashed because we expect it to crash because we don't have any shellcode or we don't have anything legit going on here. But I want to actually set a breakpoint on this address. Okay, my breakpoint is there. I just rerun. Yeah, messed it up. I think I have to restart this service again. All right, BP to set my breakpoint, and then BL to list. So sweet. The breakpoint is there on that instruction. Just one more time, I'm going to hit U to actually disassemble this instruction, or the instructions at this address. It's still jump ESP. That looks good to me. Hit G to continue. And now let's hit up arrow a few times, and let's run our exploit. And we see that our breakpoint was hit. So it is about to execute this instruction to jump onto the stack pointer. Let's do a dd esp. So the stack pointer currently contains our C's, and in x86 C or hex 43 is an actual instruction. It is an actual opcode. If I do esp, you can see that 43 means increment the EBX register. So if you come here and we look at EBX, see it has the value 0. Now I'm going to hit P just to set forward one instruction. So we executed our jump. We're currently at the stack pointer and we're about to increment EBX. So we see here EBX is 0. Hit P to continue. Now EBX is 1. Do it again. It's 2 and 3 and so on and so forth. Now if I hit a PT to just continue execution to the next return address, we see how much this is incremented, right? It was 0, 1, 2, 3, 4, 5. Now it is hex 18C. I have no idea what that is. From here, Python 3. What is hex 18C? 396. So we sent 400 C's and we see 396 of them have been written to the stack. So this is awesome. This is great progress. So now what we want to do is once again close out of WinDbg and restart the service before we forget. Start it up. And we want to replace these C's with our actual shellcode. So this is the dealer's choice at this point. You can have shellcode that simply opens up calculator. You can have shellcode that creates a reverse shell or creates some type of bind shell, some listening shell on the service. It's up to you how creative you guys want to get. I'm going to be using MSF Venom just to create a very simple listener. PC battery's running low. So I'll be running this very simple MSF Venom command to generate my shellcode for me. So the payload will be a Windows shell, so regular CMD. It'll open up a listening connection, a listening socket, right, on localhost and port 4444. And then I don't want my shellcode to have any of these bytes in there. Don't have a null byte, don't have a new line, don't have a carriage return, anything that might like truncate or mess up my shellcode. I don't want it there. And then output the format in Python, so it makes it easier for my exploit proof of concept script, and name the variable shellcode. So we hit the enter key, and this will take a couple seconds to run. We see our payload size is 353 bytes. So that's important. That's why we looked at how many bytes we can write past our instruction pointer overwrite. We saw we were able to get we tried 400, but we were able to get 396 C's or 396 bytes. If our payload was very big, if it was 500, 600 bytes, we wouldn't be able to store a payload after the instruction pointer overwrite. We'd have to store it somewhere else in the program. So we can just grab this and we can slam in our shellcode. It's kind of funny how this one byte is on a line by its own, but that's fine. And now we can get rid of this and say payload plus equals shellcode. Let's save this. Before I run anything, let me actually open up PowerShell. Get net connections. Let's get net TCP connections. And I always forget the syntax for this. Let's do a help. Let's filter on local port 4444. And you see currently there's nothing listening on 4444, but after we run our exploit code, we should see that it does have a listener installed. Now we can be, if we're particularly feeling confident and we don't want to debug or look at our exploit within WinDbg, we can just run this. So let's try. Let's see if we can get lucky first try and just run this exploit code and see if it works right away. are if we need to do some further troubleshooting and analysis. So the exploit should have run now. Oh, we do get an error. Let's go back to Visual Studio Code. Not sure what it did not like. Let's restart the service again. Let's go to it in a web browser just to confirm that it's up and running. Okay, so this works. Let's run our exploit code. Why is it crashing? What is it not liking? Well, we didn't get it in our first try, so let's open up debugger. Okay, so my debugger is open. I recreated this breakpoint on our jump ESP instruction. And now let's run this code, this exploit proof of concept one more time. And we should see a hit in our debugger. So yes, so we hit the breakpoint. I'm gonna do a DD ESP. Let's do L80. Just so we can look at some of the instructions. So D9, DD, 9BBF. I'll come over here. Look at my shellcode. Written correctly? It looks like some of the bytes aren't actually getting written there. And now that I look at it, I did make an oops. So, okay. It looks like some of the shellcode is not being written to the stack correctly. Usually you don't want to just slam in your shellcode. We want something called a mop sled. We want a little bit of buffer. We want a little bit of wiggle room between our instruction pointer overwrite and our shellcode. So we're going to do hex 90, which is the no op instruction, which basically just means go on to the next instruction. It's just padding. It's just filler. So let's slam in about 24 of these. Let's remove this. Let's restart our process. Because we could see that some of our shellcode isn't successfully being written to the stack. So let's add in a little bit of padding with a mop sled. Let's be bold and just up arrow enter, send the payload. There we go. Now we can see we successfully opened up a local listening port on quad 4s. So we basically backdoored my computer. We made a backdoor for us to connect into later. You also could have done a reverse shell and caught your handler and metasploit or something like that. So sweet. So that's why it wasn't working. That's why it's always good to open up your code in a debugger, because you think it might be working one way, but in actuality, it's working some other way. So for whatever reason, the first like 4 bytes were being cut off. So adding in this little bit of padding for a mop sled did the trick. And we could have also include our exploit, our shellcode in the beginning of the buffer, but I just like doing it everything. So sweet. We successfully wrote a working exploit. And I do have this available, the proof of concept, on my GitHub. And it is a little bit cleaner, I believe. But that's really it for this video. Thanks for sticking around. I know this was a bit longer. Hopefully it wasn't too boring. Hopefully you guys found this a little bit helpful or fascinating. Capture the flags, I love them, and I'll keep making capture the flag videos, obviously. However, it is nice to kind of look at actual applications, real world software, and looking at modern stuff, or like things to do with the kernel, can be a little bit intimidating. So taking a step back and going on websites like exploitdb that do have known vulnerable software that you can kind of just dig through and practice your reverse engineering. Now today, we really just used a debugger and we did dynamic analysis. However, maybe you want to look at some of these inside of a disassembler, like Ghidra or IDA Pro and things like that, and just look through the different assembly instructions. So if you guys like this style of video, I'll make more in the future, and I'll kind of breeze through them a little bit quicker. I never know what pace to go at. Sometimes I'm like, maybe I need to go slow and explain every single step, because you never know who's watching. Maybe this is their first introduction to exploit development or reverse engineering, or like, you guys are all seasoned professionals, and maybe I can kind of just speed through some of those beginner parts. So I'm still playing around with it. I do have an exploit development review video coming up soon. I've been taking an exploit development course, and it's really good, and I want to kind of just share it with you guys. So expect that in the very near future. But as always, guys, thank you for sticking around. Thank you for watching. And as always, take it easy, and I'll see you guys in the next video.